start. So the topic of today's video will be the same, continuing from the last video. That is linear non-homogeneous PDE with constant coefficient. In the last video, we solved this equation when the right hand side was considered as 0. At this time, we will be solving the questions when the right hand side is non-zero, right? So writing my linear non-homogeneous PDE in this form, I consider f d comma d dash and z is equal to g x comma y. This was our equation number A, right? And f d d dash z is equal to 0 if the right hand side is given as 0, and let it be equation number B. As we already know that the solution to this equation B is actually the complementary function of equation number A, okay, right? Then solution to A is given by Z is equal to CF plus PI. And what is CF? CF is a complementary function, right? That is the solution of this equation number B. By equating this left hand side to 0, we get complementary function. And to evaluate particular integral, we focus on this right hand side term of equation number A, that is gxy. We have several techniques to evaluate the particular integral, as we did in our last videos, linear homogeneous PDE with constant coefficients. Okay, so okay, now we will be discussing the case for particular integral or particular solution, because this has been already been discussed in our last video. So focusing on particular solution for different cases of gxy, right? We know that particular solution is equal to 1 over f of d dash, and here we have gx comma y, right? And depending on the nature of this gxy, we have 2 or 3 types of cases, right? So first I will be taking the case when case 1, if g x comma y is equal to some exponential function e raised to the power ax plus by, right? So then particular solution is given by 1 over f d dash and e raised to the power ax plus by, and the result is 1 over f a b and e to the power ax plus by, means this b is replaced by small a and d dash is replaced by small b, provided this denominator is a non-zero value, provided f of ab is not equal to 0, right? Okay. Case 2. Should I prove this? However, it has already been proved in for homogeneous case. The proof is almost the same. Let me give another way to prove it, right? Proof. Since d operator d operated on a e to the power x plus by will give differentiation of this function with respect to x, right? That will be a times e to the power ax plus by, right? Okay. Now if I put r here, then I will be getting a to the power r e to the power ax plus by. That is easy, right? You can see this. And d to the dash s means derivative with respect to y s times of e to the power ax plus by will be b to the power s e to the power ax plus by, right? You can verify these results by yourself. Also, if I write d to the power r and d dash s e to the power ax plus by will give me a to the power r, b to the power s, e to the power ax plus by, right? Means this is the mixed derivative with respect to x and y, with respect to x r times and with respect to y s times. Okay. Then we can generalize. Then f of d comma d dash e to the power ax plus by, it appears that using these three or generalizing these three, the d is replaced by a small a and d dash is replaced by a small b. So f d d dash will give f of a comma b and e to the power ax plus by, right? And now you can easily take this operator here and 1 upon fab here, or you can say that operating the operating with the inverse operator of d d dash, right? Same thing there. Then we'll get 1 over f d d dash e raised to the power ax plus by is equal to 1 over f a comma b, and here I have e to the power x plus by, provided this is not equal to 0, because fab can only be taken in the denominator if and only if this is a non-zero value, right? If and only if f of ab is not equal to 0. So this is a small proof for this. Why we substitute d is equal to n, d dash equal to b in the case of exponential function present on the right hand side. And let me perform a numerical based on this first, then I will go to case number 2, right? So taking a numerical on particularly of this case, example number 1, I have to take exponential function on the right hand side. So d minus d dash minus 1, and this is d minus d dash minus 2, z is equal to take some any function e to the power ax plus by type function, and let it be 2x minus y. Okay, right? And yeah, and you see that these factors, looking at this factor and this factor, both are linear factors, obviously, because we are doing linear equations, and they both are non-homogeneous. See, this is a non-homogeneous first order derivative with respect to x, first order derivative with respect to y, and this is 1. Okay, fine, and same for this case, right? And one more point is that these factors are already reduced to as a product of linear factors. Luckily, this time we don't have to use that exponential method e to the power hx plus ky method as we discussed in our last video. This is already factorized. We can directly write the solution. Okay. Then solution, we have d minus d dash minus 1 and d minus d dash minus 2, z is equal to 0. We have let me take the right hand side is equal to 0, right? Because I am focusing on the complementary function, the right hand side should be taken as equal to 0. Okay. Then for this part, writing solution for this part, then solution means solution to this. This is actually equation number b, right? And this is equation number a. If you compare the theory with this example, right? So writing the complementary function for this, CF will be f1, and as you know that this will become y, and this sign becomes y plus x, and this goes here e to the power x by 2, right? Plus e to the power 2x f2 y plus x, right? Okay. And you see that how many arbitrary functions are present? 2 arbitrary functions, because the second order. So this is the complementary function. Okay. And then focusing on particular solution which we are going to discuss for this case, exponential function present on the right hand side, that will be 1 over d minus d dash minus 1, and here I have d minus d dash minus 2 e to the power 2x minus y. Okay. Then following this formula, right? Okay, just replace d by small a and d dash by small b. Okay. So you will be getting something like that: 1 upon d is replaced by 2, and d dash is replaced by minus 1, and 2 minus 1 minus 2, and e to the power 2x minus y. Right. This will be, I think, 2 Plus 1 minus 1 cancel out. 2 here we will have 2, and here we will have 2 minus 2 will be cancelled out. Plus 1, 2, 1 by 2. So e to the power 2x minus y by 2, if I am not mistaken. Okay, yeah, right. So now writing the complete solution. Therefore, z is equal to cf plus pi will be the complete solution. You can add them. Okay. So this was the case. In the right hand side, this is an exponential function e to the power x plus by. Then moving on to our second case, case number 2. Let me start from here. Case 2. Case 2. If right hand side of this equation number A, if gxy is actually sine ax plus by, right? Then this particular integral formula becomes then ps is equal to 1 over fd b dash, and here I have sine of ax plus by is equal to, in this case, I should write it as f d square d dash and d dash square. This is solved. Sine ax plus by. Okay. In that case, the result comes out to be f minus a square minus ab and minus b square and sine ax plus by. So this will be the particle solution. But remember that the operator has to be written in this form: d square dt dash and d dash square, means the second order derivative should be present there, right? And how this formula can be proved, I will show you in a small proof. Now to prove this formula, okay, now performing my operator d on this function sine of ax plus by. Since we know okay, that d of sine ax plus by, now differentiate it with respect to x once, then it will give a times cos of ax plus by, right? A times cos of ax plus by, and then differentiating it again, I want the double derivative, actually second derivative with respect to x, then it will be like minus a square times sine of ax plus by. You can see it is very easy. Minus a square sine of ax plus by, right? Means after differentiating it twice with respect to x, the result is actually some constant multiple of the function itself, right? That's what we want. Okay. And similarly, you can say that, or should I generalize? No, this is fine. Okay. And you also know that b dash square of sine of ax plus by will be something like minus b square sine ax plus by. This is fine, okay, right? Because with respect to y, it will be b square. Okay, fine. And moreover, d dash means you operate first with respect to y and then the result with respect to x. You can see that. Differentiate this function first with respect to y, then it will be, I think, b times of cos of ax plus by, and then differentiate the result with respect to x, right? And the result means this result of this thing, a times cos of x plus by differentiated with respect to x, that will be a b, yeah, a b or minus ab, sorry, minus ab, that will put a minus on the second step, minus ab sine of ax plus by. Now, what does it mean? It means that if your operator is a second order operator, right, here, and these all are second order operators, then this d is replaced by a and d dash is replaced by b. No, not like that. You can say that d square is replaced by minus a square, d dash square is replaced by minus b square, and d dash gets replaced by minus of ab, right? Actually, the second order operator is replaced by negative of a square if it is with respect to x. The second order derivative of with respect to y gets replaced by minus b square. The minus sign is playing a role here. Okay. So in order to generalize it, therefore we can write it as f of not d comma d dash this time. No, this is wrong, because we can generalize for second order derivative, right? So this time it should be f of d square and then this mixed derivative d dash and then d dash square, right, of sine of ax plus by. It gets replaced by f minus a square and then d dash is replaced by minus ab and this minus b square of sine ax plus by, right? And then bringing this operator in the denominator and this value, provided this value is non-zero value. Here I have to mention this thing here also. This denominator is a non-zero, provided this value denominator f of minus a square minus ab minus b square is equal to non-zero, right? Okay. So now if you bring this operator here, that will give the same result. Okay, so 1 upon f of d square d dash square of sine ax plus by is equal to 1 upon f of minus a square minus ab minus b square sine ax plus by. This is a small proof for that, right? And same is the situation if you write gxy is equal to cos of x plus by, the result is similar. I will write this case here, this case number 2, right? I should put as case number 2a, and here I will have case number 2b. If gxy is cos of ax plus by, then particular solution is equal to 1 over f, same thing, d square d dash square cos ax plus by, right? And the answer is 1 upon f of minus a square minus ab minus b square cos ax plus by, right? And this is same result. And same condition, provided the denominator is a non-zero, minus a square minus ab minus b square is not equal to 0, right? So treatment will be same, either it will be a sine function or a cosine function, the treatment will be same. Okay, so taking next example based on this, should I start from here? Okay, example number 2, right? And that is d square minus d dash z. Okay, this time I have taken this factor, right? First it is linear, okay, that's fine. And the second thing is that it is non-homogeneous, right? And third thing is that it is non-factorizable as a product of linear factors, right? Okay, and if I take cos of 3x minus y here, okay, right? Then solution, I mean, this factor d square minus d dash is not further factorizable as product of linear factors, and obviously this is not a linear factor, right? Because d square is present here. Linear in that sense that treating it as a polynomial in d, right? Or you can say that putting d equal to m and d dash equal to 1, think like that. It is not a linear factor. Linear factor is of the nature d minus md dash minus alpha, right? Like this one. This is linear factor, d minus 1 d dash minus alpha, right? If I have some power here, d square d dash square to the power something, then that is not linear, right? Then I have to approach like this, that z is equal to capital A e to the power hx plus ky be the solution of what? of d square minus d dash z equal to 0. And please see the details how this method works in our last video, right? And I am not doing that in detail, and that gives me, after substituting this z here, I will get something like that, h square minus k equal to 0. Then the solution is the solution. Then I am writing directly the CF. CF is equal to, that will be summation I a I e to the power hx plus ky, right? And h square is equal to k. Okay, h I x plus hi square y, right? Where h and a are arbitrary constants. Okay, this is CF for this equation. Okay, now focusing on the particular solution, right? Particular solution is equal to 1 upon d square minus d dash, and here I have the right hand side is cos of 3x minus y. Okay, now see this formula. Formula definitely needs d square, dd dash and d dash square terms in the denominator, right? But if you see this, we have d square, right? That is fine, but we have d dash. Okay, and this formula tells us that d square should be replaced by minus a square, dd dash with minus ab, and d dash square with minus b square. So I have to replace d square by minus of a square, and what is my small a? Small a is actually 3, and what is minus of 3 square? That will be minus 9, right? It is, first we will square this term, then we'll put minus. It is not minus a whole square, it is minus a square. Then you will be getting something like this, 1 over minus 3 square minus d dash using this formula, and cos of 3x minus 1. Then you can take minus common, and that will be minus common, 1 upon, I think that will be d plus d dash plus 9, sorry, d dash plus 9, and here I have cos of 3x minus y. Now what will I do? I don't have d dash square or d square term here. I have only have d dash, right? And that cannot be replaced by a or b. I have to maybe multiply it d dash minus 9 and d dash minus 9 in the numerator and denominator, right? In order to get d dash square term in the denominator. So one thing I can do is that multiplying d dash minus 9 in the numerator as well as denominator. As I said earlier, that these operators means fdd dash, it behaves as a single entity. It has its own existence, and it can be taken in the numerator, denominator, and you can even rationalize by something of fd dash, d dash. You can multiply the numerator and denominator by d dash minus 9, right? So that is fine. Okay. Now that will become 9 minus d dash, and on the denominator between d square minus 9 square, that will be 81, and cos of 3x minus y. Then since I have got d dash square term in the denominator, so I can substitute d dash square by this minus b square term. Okay, and remember that what is my b? B is actually minus 1. I have tried it. I replace d dash square by minus of b square, and actually my b is minus 1 square, right? B is actually equal to minus 1. Then it will become minus 1, I think, right? Then it will become 9. And one more thing, you can take cos here, multiply this cos, or this operator gets operated on cos function. Okay, 9 times cos 3x minus y, and d dash of cos 3x minus y, and the denominator will become now minus 1 minus 2 minus 82, right? And as soon as it becomes a real number, right, I take this function over the head of this value, right? I do not do this step here because this is still an operator. You cannot write cos over the head of this operator, right? So as soon as you get this as a real number, as I got this in this step, then I can take this cos here over its head, right? Okay, then it will be 9 times cos 3x minus y, and that will be differentiating it with respect to y. It will give me minus sign, and that will be plus, and then again with respect to y will be again another minus, then minus sine 3x minus y, and whole divided by 82 minus 82, right? And this minus will get absorbed here. This term will be minus, and this will be plus icon, right? So this is the particular solution, and then z is equal to Cf plus Pi is complete solution. Pi or Ps, particular solution or particular integral, both are correct. Okay. So taking our next case, that is our case number 3. Case 3 is if the right hand side gxy is equal to x to the power m and y to the power n, right? Then Ps is equal to 1 over f d dash, and here I have x to the power m, y to the power n is equal to f d dash whole to the power minus 1, and then x to the power n, y to the power n. And then you remember that thing, that we apply the binomial expansion of this thing, f d dash, right? Ascending powers of either d by d dash or d dash by d, and then operate it, right? Okay. This is the same as we discussed in our last of our videos for the homogeneous case, right? Expand f d dash whole to the power minus 1 in ascending powers of d over d dash or d dash over d, right? And evaluate. Okay, right? And one more thing, that will give rise to 2 different kind of PIs. If you expand in powers of d by d dash and or in powers of d dash by d, then maybe 2 possible particular solutions for us, the right hand side, right? Okay, so let me take an example of this. Example number, I think, let me call it example number 1 to 3. Example number 3. Okay, right hand side should be of this nature. Then let me take d square minus d dash minus 1, and here I have z is equal to, the right hand side can be taken as x square y or x y cube, anything. Let me take it x square y. Okay, right. Now see that, focus on this thing. Is it factorizable? Means it can be factorized as a product of linear factors, yes or no? No, right? No. So I have to use that e to the power hx plus ky solution, right? Okay. Solution. Now focusing on this operator, considering that operator, let d square minus d dash minus 1, z is equal to 0, and it is non-factorizable as a product of linear factors. So I have to let z is equal to a times e to the power hx plus ky with the solution, be its solution. Then I will plug in this value here, and I will be getting this complementary function that should be summation I a I e to the power, that will be h square minus k minus 1, and the value of k will be h square minus k will be replaced by h square minus 1 y, and here we have hi x plus, right? Yes, right. So this will be the complementary function, and then particular solution will be 1 over d square minus d dash minus 1, and the right hand side is x square y. Okay, now if I take this minus common, then I will write it as minus, because it has to be made as plus 1 in order to expand it in powers of d by d dash or d dash by d. So I have taken negative common out of it, and it will be 1 minus this d square minus d dash. Okay, then it will appear in the numerator. That will become 1 minus, since this has been taken common, and d square minus d dash whole to the power how much? Minus 1, right? Okay. One more thing, ascending powers of d by d dash or d dash by d, is it necessary? No, in this numerical this is not necessary. So ascending power of d by d dash or d dash by d, or anything, maybe or it 1 or expand one more, and or expand 1 minus g of dd dash whole to the power something, that will be minus 1. Okay, so this is the case for this. This is not in powers of d by d dash, not in powers of d dash by d, but I think precisely this case 1 minus g d dash. D is a new function, right? Okay, that's fine. 1 minus or 1 plus minus. Okay, plus minus, both are possibilities. Okay, even this is an open possibility. Power can be plus minus 1 or minus 2 near the power, right? Should I write it as minus 1? Minus. Okay, that's fine. Then the expansion will be minus 1 plus d square minus d dash, and then again plus d square minus d dash whole square. I think 3 terms are sufficient. Okay, and you know that expansion 1 minus z whole to the power minus 1, then 1 plus z plus z square plus z cube, and so on. All terms are positive, and the power of z goes on increasing, right? Now bringing this x square y everywhere inside bracket, I will be getting minus x square y, and bringing this x square y here means I have to differentiate twice with respect to x. This term, that will be I think 2y. Am I right? Right. And d dash with respect to y of this term, that will be x square minus x square. And then opening the square of this term, that will produce d to the power 4. Right. But d to the power 4 means differentiating x 4 times. But see this, here we have only x square, so that will be 0. And squaring this term will give d dash square. That will not work, because again the power is 1 and it is d dash square. Third term will be minus of 2 times of a into b. That will be minus 2 square minus 2 d square d dash. Yes, that will be needed obviously. And do not forget this thing, that you forget to write 1 or 2 terms which are of relevance from this bracket. However, 2 terms are irrelevant because we don't need them. The third term is, I have to write the term minus 2 times d square d dash. Okay, I need this term, so note this step. It is a dangerous step. Okay, and then rest is fine. Okay, bracket close, and then I will get x square y, bringing this negative inside, and then minus 2y plus x, and then this becomes plus times 2, and this operator operate this on x square y. D dash of this will be x square. Okay, 2 times 2 4, it will be 4. This is the particular solution, and then you can write the complementary function plus particular solution to get the full solution. Okay, so we have done 3 cases, and I think we can do one more case here. Means exponential function with the product of some function of x and y. Okay, let me rub it first. Case 4. Case 4. If the right hand side is gx comma y is of this nature, e to the power ax plus by multiplied by some b, and v is some function of x and y, right? This is a function of x and y, but I am not writing it because that is fine. V is fine. This is a function of x and y. Where v is function of x and y. Right. Now then, in that case, p particular solution is equal to 1 over f d over d dash and here I have this function a for x plus by v. It becomes e to the power x plus by. It on getting operated, right? It goes here, means it jumps here e by x plus by. Then 1 over f d plus a d dash plus b, and here we are left with b, right? So it indicates that the preference is given to the exponential function first, right? And rather than substituting d is equal to n and d dash equal to b, this is not the case this time. It replaces d by d plus a and d dash by d plus b, and goes out of the calculation immediately, means it appears here. Then we focus on this term only, this thing only, right? This is not our concern, right? This will be repeated in calculation, but will not be the part of calculation. Okay, we will focus on v, and depending on the nature of v, we will proceed, right? So a small proof of this formula may be given. If I write it as proof, okay, let me write it. Since d operated on this, I have this function this time, okay, e to the power ax plus by and v. Let me, and remember that v is not a constant, okay. Then applying this derivative, I have to use product rule, and that will be a times e to the power ax, or should I write Polytechnic? Okay. E to the power ax plus by means the first function as it is, and differentiation of second function dv, and then first function as it is, and the differential of second function as it is, differential of first function, that will be a times e to the power x plus by and v. I think this is fine. I have applied product rule for these two functions. Should I write it this way? Okay. Then it is actually taking common out of it. I think e to the power x plus by can be taken common, and I can write d plus a v. That is capital V. Okay. And notice that how I have written this. Actually, the purpose is to write this exponential function before the operator. And why I have written this before the operator? Because it has been differentiated already. I have used product rule, right? First term as it is, and the differentiation of second term, right? Differentiation of second term, but this is just function, right? And see here, this is already differentiated, means d will be operated on v depending on the nature of v, and exponential function has already been derivated, and that's why I have not written this exponential function here. This is a big point, that exponential function should be written first before the operator, and v has to be written after the operator. This is the operator, right? Before operator exponential function, because it has already been operated in this step, right? And since v is not operated, because we will operate d on v depending on the nature of v, right? And that's why v should be after the operator. Okay. Similarly, if I write d square e to the power ax plus by times v, let me differentiate it again and see what happens. Okay. Then d square of this thing, that will become, I think, d times, d square means d 2 times c, and d times of this thing is actually this, e to the power ax plus by d plus a v. Okay, and treat it as single term, first function, second function. This is not first function, second function, third function. No, first function, second function, because it is an operator. It cannot be treated as a function. Operator on with the function is a new function. So this should be your first function. This should be your second function. Then apply again product rule. Okay. Now see, first function as it is. Okay. And differentiation of second function, right? And then this d gets multiplied here, or d square plus ad, right? E to the power ax plus by, one second, and this will be d square plus ad v. Okay. Then plus differentiation of first function, that will be a, I think, and e to the power ax plus by, right? I have differentiated this function, and this function as it is, that will be d plus a v. Am I right? Okay. Right. Fine. Then take common, or try to write in this form. Remember that exponential function should be written first before the operator, and the operator that is left with me, that will be d square, okay, plus AD from here, and from here d AD plus A square. Okay. AD plus A square, and here I have my function V, which is still unknown to me. What is V? Okay. Okay. Then this is actually e to the power ax plus by, that will become d plus a whole square v. Right. Now we have got something that one d operated once, that will produce this result, d operated twice, that will produce a square on d plus a, and then we can generalize it. Right. Generalize d to the power r and e to the power ax plus by v will be something like this: e to the power x plus by and d plus a whole to the power r v. Right. This is r. And similarly, for d dash, we can write this result: d dash r, no, d dash s, power has to change, e to the power ax plus by times v is equal to e to the power ax plus by d dash plus b s v. It is easy to generalize this. When you see this, you can see that d to the power r is replaced by d plus a to the power r, and the exponential function goes before the operator and v goes after the operator. Right. So similarly, I want to generalize this in terms of d dash, or I may write f of d comma d dash, right, e to the power ax plus by, then v, that the answer will become e to the power ax plus by f of d plus a and d dash plus b, right, and here I will have b. Okay. Right. Now I think I got the result. Yes. Now taking this here, I did it there and this in the denominator, then I will get 1 over f d comma d dash e to the power ax plus by v is equal to 1 over f of d plus a d dash plus b, and here I will have v, and here I will have e to the power x plus by. Right. So this is the result we wanted to prove. Right. And there is no danger that the denominator will become 0, because it is still having d and d dash. It is not a real value that we can write, provided it is not equal. No, this cannot be 0, I think. Right. Okay. Then taking an example of this formula, this one, and let me take d minus 3d dash, d minus 3d dash minus 2 whole square. This is example number, I think, 4. Okay. And z is equal to some exponential function multiplied by some v, function of x and y, and it should be e to the power 2x sine 3x plus y. Right. Okay. Or y plus 3x. Right. Fine. Then solution. Now taking this z equal to 0 means this operator z equal to 0 to find complementary function. Should I write that directly? Okay. Consider d minus 3d dash minus 2 whole square and z is equal to 0, and see this is already a linear factor, and writing the complementary function for it, you can write it directly. It is very easy. Then 2, it goes in the power of e 2x f1 y plus 3x, and since the factor is repeated twice, then x multiplied by e to the power 2x f2 y plus 3x is the solution, where f1 and f2 are arbitrary functions. I'm going to particular solution. Ps is equal to 1 upon d minus 3d dash minus 2 whole square. Okay, fine. And here I have e to the power 2x plus 0y, exponential function, ax plus by, b is absent, sine 3x plus y. And since this is same, right, so d should be replaced by d plus 2, no, d plus 2, and d dash should be replaced by d plus 0. Replace d by d plus 2 and d dash by d dash plus 0, because b is equal to 0. So I will get e to the power, immediately this exponential function goes out of the calculation, remember that, because this appears here before the operator, right? Okay, e to the power 2x, and that will give me 1 over d plus 2 and minus 3 d dash plus 0, that is fine, and minus 2 then whole square. Okay, and it is sine of 3x plus y. Then it will be e to the power 2x, it will become d minus 3d dash, d minus 3d dash, and 2 and 2 will be cancelled out, square sine 3x plus y. Now focus on this thing only, this thing, right? Okay, now remember that when sine function is present here, then d square is replaced by minus 3 square and d dash square is replaced by minus 1 square, and d dash is replaced by minus a into b. Okay, but that is not the case here because we are not having d. Okay, should I open this? Yes or no? If I open this, then I will be getting, okay, I am getting 0, and see this factor. This is the homogeneous factor. See this, both are of same order, right? And then we can apply that rule also, homogeneous factor, right? Where we got 0 in the denominator, and when we got 0 in the denominator, then we have one formula that x to the power n appears here, right? I will apply that formula from homogeneous theory, and e to the power 2x, and using that formula, that will give me something like x square, because this is square term, right? And sine 3x plus y over n factorial, means 2 factorial, and the coefficient of these 1 raised to the power n 2, and I will mention that formula, right? And that formula was 1 upon bd minus ad dash whole to the power n, and here we had phi of ax plus by, and see this, if you put d is equal to a and d dash equal to b, we will get 0 in the denominator, and that's why we have this formula, x to the power n over n factorial 1, no not 1, b to the power n and phi ax plus by. Okay, use this formula from theory of homogeneous PDE. We have done this, right? This is the answer. Okay, e to the power 2x x square sine 3x plus y over 2, right? This is a particular integral, therefore z is equal to cf plus pi is complete solution. Okay, so this is the case when the right hand side is a non-zero, and I think we need some general method to evaluate the particular solution, as we did for the homogeneous case, right? So we will be finding the general method to evaluate the particular solution for any case. Means that will not depend on the nature of the function present on the right hand side. That will work for any case, right? That single formula will be useful for any gxy present on the right hand side, right? And that will be part of the next video. This video, thank you so much.